One type of a reaction which we're going to be taking a look at is a precipitation reaction. We've seen those before, but we're going to spend a little bit more time on what precipitation reactions actually are, what is actually interacting. But before we can do that, we need to expand just a little bit on what ionic equations are. So for now, what we've seen so far is we've seen molecular equations. We've already seen those. So we have molecular and ionic equations. And we're going to take just a few minutes and talk about the difference between the molecular and the ionic equations, what those actually are. We use chemical equations to help us describe chemical reactions. For a reaction involving ions, we have a choice of chemical equations depending on the kind of information that we want to convey. We can represent such a reaction by either a molecular equation, a complete ionic equation, or a net ionic equation, and that's what we'll be talking about, the difference between those three. To illustrate the difference in the different types of equations, consider the preparation of precipitated calcium carbonate. Now, we actually perform this lab. The white powder that results is chalk, but it's also used as a paper filler to brighten and retain some ink, as an antacid. You've probably seen that in Tums, and as a mild abrasive in toothpaste. One way to prepare this compound is to react calcium hydroxide with sodium carbonate. So let's take a look at a molecular representation of this, or the molecular equation. So molecular equation we said that we are taking calcium hydroxide, so CaOH2, which is in solution, so aqueous. So we have calcium hydroxide, aqueous, plus sodium Na2CO3, so sodium carbonate, which is also aqueous. And we said what we'll get out is this precipitate of calcium carbonate, which is solid, and sodium hydroxide, OH, which is also aqueous. So this is the molecular equation for it, which is, by definition, and we'll go ahead and write this definition out, the chemical equation in which the reactants and the products are written as if they are molecular substances. So reactants and products are written as if they are molecular substances, even though that they may actually exist as ions. So we can put that in maybe parentheses and something next to it. So even though they may actually exist as ions. Okay, so what that literally means is that we write it literally as a compound. We don't separate these out as calcium ions and hydroxide ions. We just write that it's calcium hydroxide and it's aqueous. We have sodium carbonate, which is aqueous, yields calcium carbonate solid, and then 2 sodium hydroxide, which is also aqueous. The molecular equation is useful because it is explicit about the reactants and the products. So this is explicitly defines what is reacting, ing, and what are the products. And we've done this many, many times before, just we never actually stated it explicitly like that. But the equation says that you add aqueous solutions of calcium hydroxide and sodium carbonate to a reaction vessel, and the result of the reaction is the insoluble white calcium carbonate, which forms in the solution. That is, calcium carbonate precipitates. After you remove the precipitate, you are left with just a solution of sodium hydroxide. The molecular equation closely describes what you actually do in the laboratory or in an industrial process. But although a molecular equation is useful in describing the actual reactant and product substances, it does not tell you what is happening at the level of ions. So let's put a star or highlight it, bold it, whatever it is that you need to do. Does not tell you what's happening to the ions. Star it, bold it, highlight it. Molecular equations just tell you what is reacting and what your products are. So even though that they are useful, we may want to look a little bit further in detail. Let's see, yeah, the molecular equation doesn't give the ionic theory interpretation of the reaction. Because that type of information actually is useful, you often need to rewrite the molecular equation as an ionic equation. And what we come to then are something known as complete ionic equations. So again, consider the reaction of calcium hydroxide and sodium carbonate. According to our rules in the table that we give it, the solubility rules, both are soluble ionic substances. So let's just go ahead and write this out again. We've got calcium hydroxide, which is aqueous, and sodium carbonate, which is also aqueous, to yield calcium carbonate, which is solid, plus sodium hydroxide, which is also aqueous. So according to our rules, both of these are soluble ionic substances and therefore strong electrolytes. And again, if something is a strong electrolyte, then they readily dissolve in water. They go into solution as ions, or they completely ionize into solution. So each formula unit of calcium hydroxide forms one calcium ion and two hydroxide ions. So if we really want, we could show like, some sort of a bridge saying that every single one of these, we know from the molecular equation that because this is an electrically neutral compound, we have 2, or 2 plus for the cation, which is aqueous. And in addition to that, we have the hydroxide ion, which is also aqueous. So when we're going from a molecular equation into a complete ionic equation, we're just separating these substances out into their constituent ions. So then we can do the same thing for sodium carbonate as well. We carried through with that plus sign, and we know sodium to have a +1 charge, or a plus charge. So this is aqueous. And carbonate, CO3 2-, which is also aqueous. And we're going to start running out of room here. And then we continue to break these up into their ions. So this yields calcium carbonate, Ca 2+, aqueous, plus CO3 2-, aqueous, plus Na plus, which is aqueous, and hydroxide, which is aqueous. Okay, so now what we have is we have the complete ionic equation. Taking a look at this thing, we notice that it is not balanced in terms of hydroxide. So we could put a 2 in front of the sodium over here, 2 in front of the hydroxide, 2 in front of the sodium, 2 over there, and now everything's all nice and balanced. So looking at the complete ionic equation, we can see that the reaction mixture begins as a solution of 4 different types of ions: calcium, hydroxide, sodium, and carbonate. We can take a look at the product side of the equation. One of the products is the calcium carbonate. If we actually do have a solid, if we know that this is going to be a solid precipitate, we can actually rewrite this whole equation and just leave calcium carbonate as that. We can say calcium 2 plus. Make sure you leave yourself plenty of room, because they end up taking up a lot of space. And 2 sodium aqueous plus carbonate yields calcium carbonate, which is solid, and then the sodium hydroxide. So 2 sodium, which is aqueous, and 2 hydroxide, which is aqueous as well. So the purpose of such a complete ionic equation, and we need to bold this, highlight it, star it, is to represent. So the purpose is to represent each substance by its predominant form in the reaction mixture. Start it. So for example, if the substance is a soluble ionic compound, it probably dissolves as individual ions, so it is a strong electrolyte. In a complete ionic equation, you represent the compound as separate ions, as we've seen before. If the substance is a weak electrolyte, it is present in solution primarily as molecules. So keep that in mind. If it is a weak electrolyte, it is present in solution primarily as molecules. So in other words, they don't dissolve in water. So you represent it by its molecular formula. If the substance is an insoluble ionic compound, you represent it by the formula of the compound, not by the formulas of the separate ions in solution. Thus, the complete ionic equation, we'll go ahead and write a definition for this thing, a formal definition. The complete ionic equation is a chemical equation in which strong electrolytes, such as soluble ionic compounds, are written as separate ions in the solution. Okay, easy enough. So you represent other reactants and products by the formulas of the compounds, indicating any soluble substances by aqueous after its formula, and any insoluble solid substances by the S. So we put the phase label S after its formula. Now, in the complete ionic equation representing the reaction of calcium hydroxide and sodium carbonate, some ions, hydroxide and sodium will notice appear on both sides of that equation. This means that nothing happens to these ions as the reactions occur. They are called spectator ions. So what we end up getting is this net ionic equation. So in a net ionic equation, we have these things called spectator ions. And by definition, again, the spectator ion is an ion in an ionic equation that does not partake in the reaction. So a spectator ion is an ion in an ionic equation that does not participate in the reaction. Okay? You can cancel such ions from both sides to express the essential reaction that occurs. So let's take a look at what that actually looks like. Again, we're going to use the calcium hydroxide and sodium carbonate. So we'll go ahead and rewrite the complete ionic equation. So we have calcium, Ca2+, which is aqueous, plus 2 hydroxide, which is aqueous, plus 2 sodium, which is aqueous, and carbonate yields calcium carbonate, which we said we can keep that just as solid, plus 2 sodium and 2 hydroxide. Okay, so here is the complete ionic equation. Okay, kind of lengthy. And what we're actually interested in is we're interested in those ions which are actually participating. Okay, so what we can do is we can take a look at the reactant side and go, okay, do we have free calcium? Okay, we've got free calcium over here. Do we have free calcium over here? Nope. Okay, so that one must be participating. We've got hydroxide. Is there another hydroxide? Yep, right there. So we'll go through and we'll cross off those ions. And then we'll look here, we'll say, okay, do we have sodium? Yep. Do we have free sodium over here, or aqueous sodium? Yep, sure do. We can cross those out. Do we have any free carbonate? Nope, that's locked up in that precipitate. So after we go through and we cross out the things that are free ions on the reactant side and the product side, we just write what's left. So we say, okay, we have calcium, Ca2+, which is aqueous. Those are gone, that's gone, plus carbonate, CO3 2-, which is aqueous, yields, and then the only thing that's left over here is solid calcium carbonate. Okay, so what we've done is we've gone from a complete ionic equation, which is that guy, crossed out the spectator ions, so those that actually are still in solution or that are still aqueous, and what we're left with down here is our net ionic equation. Okay, so by definition then, the net ionic equation, we'll give a formal definition to this, the net ionic equation is an ionic equation in which the spectator ions have been removed. So an ionic equation in which the spectator ions have been removed. Okay? So it shows that the reaction that actually occurs at the ionic level is between calcium ions and carbonate ions to form a solid calcium carbonate. All the other ions which we crossed off are actually not participating in the reaction. It's not to say that they aren't important, they're just not forming the solid, the precipitate. Okay? So from the net ionic equation, you can see that mixing any solution of calcium ion with any solution of carbonate ion will give you this same reaction. For example, the strong electrolyte calcium nitrate dissolves readily in water to provide a source of calcium ions. According to our solubility rules, calcium nitrate is soluble, so it goes into solution as calcium and nitrate ions. Similarly, the strong electrolyte potassium carbonate dissolves readily in water to provide a source of carbonate anions. Again, according to the solubility rules, potassium carbonate is soluble, so it goes into solution as potassium and carbonate ions. When you mix a solution of these two compounds, you obtain a solution of calcium ions and carbonate ions, which react to form the insoluble calcium carbonate. The other product is potassium nitrate, which is a soluble ionic compound and therefore a strong electrolyte. So let's take a look real quick at the equation for this. In our example, we had calcium nitrate, so Ca NO3 which is aqueous, and potassium carbonate, which is also aqueous, again yields that solid calcium carbonate and 2 potassium nitrates, NO3 aqueous. Okay? So here's just another example of how to write a complete ionic equation. So again, we said, okay, according to our rules, our solubility rules, these will dissociate completely in solution to yield calcium. So we'll go ahead and write our little tree here. We'll have calcium ions, Ca2+, in solution, so aqueous, plus NO3, 2-, which is aqueous, plus, we're going to break this one up again, potassium, which is aqueous, and carbonate, CO3, 2-, which is aqueous, yields. We know that this is solid, or it is the precipitate, so we can just rewrite this exactly as it is. Calcium carbonate, keep the phase label solid, plus, and then we can split this up. We have K+, which is aqueous, plus NO3-. Oops, I may have made a mistake here. Minus. There we go. That's a little better. And this is also aqueous. Okay, so we went from the molecular formula down to a complete ionic equation. So this is the complete ionic. So it's all the ions that are actually involved. So the complete ionic equation. And now we'll look again. Ooh, we probably should balance this thing first here. So we need 2 nitrates, 2 potassium, and again 2 potassium, 2 nitrates. And to go from the complete ionic equation into the net ionic equation, again we just look and see if we have free ions on the reactant side and the product side. So we go calcium, okay, that's aqueous, we have calcium over here. Nope, that's locked up in that solid. Nitrate, nitrate, yep. So we'll cross those out. Potassium, yep, aqueous potassium over there. Carbonate is locked up in the calcium carbonate over there. So then we just rewrite this with the spectator ions being removed. So calcium, Ca2+, aqueous, plus carbonate, yields calcium carbonate, which is solid, and that's the only thing that's left on that side of the equation. So note that the net ionic equation is identical to the one obtained from the reaction of calcium hydroxide and sodium carbonate. The essential reaction is the same whether you mix solutions of calcium hydroxide and sodium carbonate or solutions of calcium nitrate and potassium carbonate. The value of the net ionic equation is its generality. For example, seawater contains calcium ions and carbonate ions from various sources. Whatever the sources of these ions, you expect them to react to form a precipitate of calcium carbonate. In seawater, this precipitate results in sediments of calcium carbonate, which eventually form limestone.